All right. Okay, so now we are marching on. We've been focusing a lot on absolute performance estimation, and so we are now moving on to relative performance estimation, which is really going to be more practical, especially in things like your final project, where you're not going to be focused so much on getting a perfect simulation model to be a perfect proxy for the real system, but instead maybe taking two imperfect simulation models that capture the qualitative features of, say, two assembly line techniques, for example, and you just want to compare and say which one is better. You don't necessarily want to know exactly how much better, but you want to say, do I see a significant effect of this change? So that's what we mean by relative performance. So that's what we'll be getting into today. Just as an overview of everything that's out there. So there's still ICA L, which is the last kind of new content-based ICA out there. But there's also this new one, ICA MB, which is meant to be a final exam review. And this is just like in the midterm final exam review, it samples randomly from the post-midterm ICAs. And so you'll see a lot of questions you've seen before. You can take it multiple times. I think it's worth 3 times as much as a normal ICA. So it's a great way to sort of make up points on the ICAs while also reviewing for the midterm. It disappears the day of lecture M, so right before lecture M. So it's meant to help prep you for midterm final exam questions. So for that final exam review, you'll maybe have some things to ask. And then, but then a practice version then becomes live, so you can continue to practice that until the final exam. Now, I wanted to mention, and this is an announcement I put on Canvas. I have a feeling that some people are going to realize that they have a lot of final exams that last week, because there's this thing called Innovation Week, which they've put during the original finals week, and then the rest of December is this innovation quarter, and it's a way to sort of maintain continuity with students between the 2 semesters, and sort of an optional semester with some other curriculum and things like that. Because they cannibalized finals week, they're telling us we can't put any of our finals during finals week, which is why you're getting packed in with a lot of final exam and final projects in that last week of regularly scheduled classes. So this final exam is scheduled for Thursday, and then I'm having this phase 2 where you get this kind of 20% of your final exam is kind of an open book collaborative take home. You don't have to do it with Respondus thing on the Friday after that. Now, I'm sure I'm going to get some students saying that they have a lot of exams on Thursday or Friday or both. Now, we are not technically allowed to offer any proctored final exams during finals week. So I'm not sure if what I'm about to do is technically allowed, but because it's an option, I'm hoping it is. And so I guess I'm saying that if you like this option, keep it quiet, because I have a feeling that I might be told not to do this if it was found out that I was doing this. So as I announced, if you go onto Canvas and then go to the people and then go to groups, you'll find there is a final exam group set. And everyone by default has been put into the early group. That's the Thursday, Friday group. If you would like to take your exam a couple days later on Monday and Tuesday of the originally scheduled finals week, then you can move yourself into that group up until the end of this month, basically up until December 1st. And after December 1st, then I'm going to freeze that so that those groups will be set. Whatever group you put yourself in, those will be the only days you're allowed to take that exam. So if you take it Thursday, Friday, you don't get to make it up on Monday, Tuesday. If you elect to take it Monday, Tuesday, it will not be available to you Thursday and Friday. So that way, anybody who wants to take their exam a few days later still gets the benefit of the stage 2 exam, the kind of group exam. And you can even on Canvas see who else is signed up for that later exam if you want to see who's available to collaborate on their stage 2 of that final exam. So that's what I'm doing, giving you the option to either take it by default Thursday and Friday, the last week of regularly scheduled classes, or you can elect to put yourself into the Monday, Tuesday group where you take it on the Monday, Tuesday of the original finals week. But again, I don't think I'm technically allowed to offer you any exams during the finals week because I'm making it an option. I'm hoping this is a useful loophole, but if it's found out that I'm doing this, I might be told that I'm competing with Innovation Week, and I might be told to cut that out, and then I'd be forced to then load everything up during that last week of class. So, so that's something that I've announced on Canvas and on Slack. There's some instructions there. Again, you just go to People under Canvas, and then from there you can go under Group, which is like a tab under the People, and then you can find the final exam groups, and you can move yourself from the early group into the late group if you prefer. I think maybe already one person has done that. All right, are there any questions about that? Just because it's kind of new, it's something special for this semester. Okay. Yes, that's right. So there's a question in the chat. So we would still have the 20% retake. Yes, I wanted to make things as identical as possible. So if you elect to take it during the Monday, Tuesday final week, Monday will be your 80% stage 1, and Tuesday will be your 20% stage 2. So it'll be identical to the Thursday, Friday, but it'll just be shifted to be Monday, Tuesday. But the number of people who will be taking the 20% on Tuesday, you know, may be low or it may be high. So that's kind of the only difference, the population. Okay, great. And then if you're looking for, you know, other study resources, once you take that final exam, the compliance check, you know, it's just to make sure everybody's Respondus lockdown browser is still working okay. Once you take that, that will unlock the final exam module. There are several sample exams, there are some extra problem sets, and other resources there too. So make sure to take that compliance check module to make sure you're still up to compliance with Respondus lockdown browser, and then you should get access to that. So several, if I remember correctly, several sample final exams, including the one from last fall, which was a Scantron exam, which will probably be the closest to what you'd expect this semester with the online Canvas-based exam. Okay. There's a reminder, J2 is available. It is the final homework assignment. It is an arena-based homework assignment where we revisit the inventory problem, the Bucky's. You know, I think Bucky was the inventory checker, so they referred to there's Bucky as somewhere in the title. And what I'm asking you to do in that one is just to go into you can either use the old school blocks or the newer blocks in Arena. And I think I provide you the an implementation already done with the old school one, but you're feel free to use a new one. And then you have to make some modifications. So you add some I think some stochasticity in where there wasn't, or was it just purely determinism before. You change, I think, some of the distributions on things that were already there. And then you play with the decision variables. And I basically ask you to optimize the inventory system. So I think you're choosing those two. Remember, I think that one was the NM inventory. So you're choosing how many to order and what to, or when to order and what to order up to. And so you're optimizing those two parameters. And so you can either do that by hand, or you can use the process analyzer or OptQuest, which will be introduced in Lab 10. So Lab 10 would normally be assigned this week because Veterans Day was yesterday. Then I extended Lab 9 into this week so that you can turn Lab 9 into this upcoming weekend. And then Lab 10 is formally assigned next week, and then do the Sunday after that. I encourage you to start Lab 10 sooner if you can, if you choose to. Remember, there's, I think, one dropped lab, so a lot of people will skip a lab, and so it's natural to skip the last lab. The reason you might not want to skip this last lab is that there are 50 points possible. So there's 20 bonus points possible in this lab. It's basically 2 labs built into one, where the first lab describes sequences, which provide a useful programming tool in Arena to do more dynamic things with if you've got multiple elements, and sometimes you don't want them to flow in a particular order. Sometimes you want to mix that order up dynamically, maybe so that certain types of entities go through in one order, but then other types of entities maybe skip a step or go through in a different order. Then sequences allow you to do that in Arena. Part 2, which again is almost like a second lab, introduces batching, signaling, and holding. And even if you decide that you don't want to compete for these 20 extra bonus points, I really encourage you to take a look at this batching, signaling, and holding. Even if you don't do the exercise, these 3 things I think can be very useful in many of your final project models. So, this batching is kind of related to that muffin sim that we did before. Signaling and holding, these are ways where you can send signals from one part of your simulation to another part of your simulation to cause that part of the simulation to temporarily hold up entities. And so this is great for traffic light simulations, for example. This is great for if you're modeling a bank or a restaurant, and once it gets full, you have to start queuing in a different area or holding people in a different area. These are drive-throughs. Drive-throughs are great examples too. You only really can fit 3 cars in a drive-through. So what happens when the queue gets above 3? Well, then you get very different dynamics, because the people who queue up can't be making orders, whereas the people who queue up at the pickup window can make orders immediately. And so you have this thing where you can get queuing before the ordering that is purely because the queue for the service window is too long for people to get access to the order window. And so there are things that you can do with signaling and holding to simulate that process. So really some cool things you can do with signaling and holding. So definitely take a look at that. And then this part 2 also introduces the process analyzer and an opt quest. And so these, the process analyzer is kind of like it's in some ways it's similar to an automated version of the output analyzer. And so in the process analyzer, what you can do is you can say, I want to run, I have a simulation model with the decision variable, and you want to then queue up and say, I want to run that decision variable or this set of decision variables at a bunch of these different settings. And I want to automate running that. And it will go ahead and run all of those. And then you can say, and I want you to measure these response variables. And then I want you to take these response variables and put them into a comparison. And you can then tell me in a statistically rigorous way which of my decision variable settings was optimal. And it can do all of that automatically for you. So it's a really, it really speeds things up. So the process analyzers are great for that. OptQuest takes it to a whole nother level, where you give your simulation to OptQuest, and then you tell it what the decision variables are, and then you tell OptQuest, and you run the experiment. And then OptQuest will decide how many replications to run, whether it needs to run more replications for certain settings than others, until it conclusively ends up deciding on a set of decision variables that are best for the response variables that you've identified. And you can even specify constraints. So not only can you say, I want the shortest wait time possible, but you need to say, but I want to make sure that the utilization never goes above 80%. And so it can watch one response variable and keep that response variable under a constraint while it's simultaneously optimizing another response variable. So OptQuest is really great. And on top of that, this here, even though it's in Arena, it's licensed, it's built by another company. If you use other programs like AnyLogic, for example, a lot of them have also licensed OptQuest. So if you learn to use OptQuest in Arena, it will be very natural to use it in many other programs that use OptQuest. So it's just a generic simulation optimization engine that's been bolted on to many other simulation programs. So another great thing to get access or to get exposure to. And then instead of having 2 open labs, I think if you look at the calendar, because of the shift, there's technically only like 1 open lab, but hopefully you're using, basically it's all about just providing you time to be able to work on that final project. So the final project, I guess now that we're getting to the point where we're starting to think about the presentations that are coming downstream, remember these are video presentations. You will, and I've got instructions on, if you've not done this before, how you in a group of 3 or 4 can use Zoom to record a video presentation of no longer than 10 minutes. You will upload to Canvas. And you'll also upload your final report at the same time you upload that to Canvas. We do that Wednesday of the last week of class. I guess technically for 2 reasons, because we have to deal with the final exam, which is after that. So it's nice to have them not overlap. But the other thing is that peer review is used in both of these. And so after you upload your presentation Wednesday night, or hopefully before that, then all of you individually will be randomly picked another individual's presentation and another individual's final report to peer review. And then you'll use a rubric that's online to score that based on what you think. And then you'll also leave some constructive comments. If your comments are constructive and your scoring is complete, then I will give you credit for the peer review, and that's part of your grade for the final project. And then I will then aggregate all those peer reviews and then use that aggregate score combined with my assessments in part of how I score the final project presentations and final reports. So the reason they're due Wednesday is so you can have Wednesday, Thursday, and Friday to take the time to watch one of those 10-minute presentations and read one of those 4-page reports and then submit your peer review. So again, so I just emphasized here that these peer reviews are due the Saturday before the originally scheduled finals week. Technically, the last week of class is both the last week of class and finals week. These are due before the originally scheduled finals week. So the Saturday at the end of the last week of class. All right, I think those are all the administrative things. Are there any questions about any of that? Okay, great. All right, so let's start out then with an attendance exercise just to get everybody warmed up on these chilly, below average Arizona days here. And so the attendance question, I'll put a link in the chat, which by the way, if you're ever watching these things asynchronously, a great way to find the attendance questions is to scroll through the chat and look for when I've posted one of these, because sometimes I skip attendance exercises. So that's the kind of secret that I'm telling you here at the end of the semester. The point estimate is equivalent to what type of confidence interval? So here I'm saying that if we, so a point estimate is what type of CI? Is it a 0%, a 95%, 100%, or is it just different than a CI? And so in your attendance response, you can either put the letter or you can put the number or the answer type. And so as you're filling out your attendance exercise, then also as we did before, it's helpful for me, you can put your answer in the chat, but then hold on, don't hit enter yet. I'll give everybody to think about this for a second. And then when I say so, then let's, those brave enough to share, it would be great to then see those answers. So go ahead and in the chat, hit enter and let me know what you think a point estimate is. So if we view a point estimate as a confidence interval, what would the confidence level be on a point estimate? So that's another way to say the question. What is the confidence level of a point estimate? And I'm seeing some answers that are coming into the chat. And I'll see if there's any other answers. All right, so the answers I see in the chat are 0%, A, 0%, 0%, and that's the answer that I'm looking for. 0% is your point estimate here. And so the kind of irony is if you give someone a point estimate, that sounds like the most confident thing that you could possibly give them because you're saying things are a point. And in reality, if you're just giving them a point and not giving them an interval, now it's one thing if you give them a narrow interval, that's kind of a different thing. But if you just say a point, you sound very confident, but technically speaking, you're giving them the 0% confidence interval. So a point estimate, if you think about it, is when you're setting alpha equal to 100%. A point estimate says that I'm rejecting everything but this point. Well, rejecting everything is setting alpha equal to 100%, so it's your significance level to 100%, which is setting your confidence level to 0%. And so really, saying it's very unlikely that your point estimate is going to be right. And so this is part of the reason I'm trying to emphasize that it's better to give intervals. You can make your intervals small, and that's how you communicate, sensitivity. But point estimates themselves are not that useful because if you run the experiment again, you might get a different point estimate. And so what we really need to communicate is not only what this experiment told us, but what interval we infer from this one experiment likely captures the true value that we're trying to estimate. That's the importance of using these interval estimates. All right, so let's do one more attendance question then. So again, I'll put the a link in the chat. And so I've got 3 confidence intervals drawn here. A is moderately wide, B is small, and C is large. So A is medium, B is small, and C is large. And so the question is, assuming that the population I'm sampling from, so the simulation, for example, has similar standard deviation in all three cases, then so basically what I'm saying is the width of these confidence intervals I'm claiming in this particular case is only due to the number of samples being taken. So if you look at these three confidence intervals, given that the standard deviation is the same across all of them, which one of them corresponds to having been calculated using the largest number of samples? So you can go in and put things into your attendance exercise response, the link. And then as well as you're putting that in there, go ahead and put them in the chat. But again, the enter key is lava. And so then we'll wait a second and then we'll have everybody reveal their responses in just a moment. So again, so which one of these three confidence intervals, the medium, the small, or the large, corresponds to the largest number of samples? So go ahead and tell me in the chat what you answered, A, B, or C, or medium, small, or large. And I'll wait for a couple answers here. I'm glad to see some different people answering from before, so that's exciting to me, sitting here in my quiet little void. And so it looks like everyone so far has answered B. B as in boy, or this small one. And that's the answer I was looking for. So the way that we gain sensitivity or statistical power is we sample more. And so rather than giving someone a point estimate, give them an interval estimate, which really shows how big, where the real population mean is most likely. But then you can sample more, and then that cranks that interval estimate down. So we can say my 95% confidence interval is this thing here. What that means is if we looked across 100 universes where I ran the experiment once, in 95 of those universes, my confidence interval would capture the true parameter that I'm trying to estimate. In 5 of those universes, I would be just unlucky and I would have had a small confidence interval and the real thing would be outside of it. But in 95 of those universes, in my one experiment, I would have got it right. And so my 95% confidence interval says, I'm willing to believe that there's a 95% chance that the real answer is in this confidence interval. And if I sample more and more, I can make that 95% confidence interval tighter and tighter. So that's the way, that's a much better way to communicate a point estimate, is to communicate a tiny interval, because then you're actually communicating to someone your level of confidence, 95%, and your level of sensitivity, how tight that is. Okay. So are there any questions about that from those two answers? Does that make sense so far? Okay. All right, and so as we mentioned last time, that the confidence interval is our way to communicate to our stakeholders a one sample t-test. Nobody likes hearing about t-tests. Those who do not have a statistical background might remember t-tests from school and thought they were just an academic thing, and so and even if they do remember those, they don't remember how to interpret them. And so confidence intervals, even if people don't remember all of the rigorous definition of what they are, they at least still make a little bit of sense. Like, okay, all you're really communicating to the stakeholder is the real value is somewhere between here and there. So it's a much more honest way. To somebody who's more statistically rigorous, you're actually communicating, these are all of the hypotheses that I can't reject with this one experiment. I ran one experiment, and this is what, if I were to run a t-test on, then I can summarize that if you gave me a hypothesis outside of this, I would reject it. And inside this, I couldn't reject. That's all a confidence interval is communicating. And this half width here, that's the reason why the critical t-value shows up there. We're just scaling the standard error of the mean. So remember, this s over square root of n, that is the variance of your estimator. If you run the experiment over and over and over again, you're going to get different estimates of the mean. They're going to hop around. And as they hop around, they'll then fill out a distribution. And this is the standard deviation of that distribution. And so the confidence interval's half-width ends up just scaling that standard deviation the same way that if you're considering a standard normal, then we can, if we know the standard deviation of the standard normal, which is just 1, then we know how far away from 0 in the standard normal we need to get in order to get all 95% of the outcomes underneath it. Well, that's what basically this is doing here, is we're scaling up the standard error of the mean by a special level, which comes from the t-distribution. And that level allows this half-width to meet our needs for this 95% confidence interval. It helps guarantee that if the hypothesis is true, we'll capture it 95% of the time. And so there are simple rules when you see a confidence interval. If your confidence interval does not include the mean, then you can take whatever that mean was that was not included and reject it. So it's a geometric interpretation of a t-test. Now, and this is just visualizing that result right here. And so I did this thing last time where I said that in all 3 of these cases here, I've got 95% confidence intervals. And so this is what up here, I've got 95%, my squiggle on here. So they're all 95%. But what I've changed here is the number of samples. I went from 20 to 200 to 2000 as I go down the list. The false positive rate, because it's 95%, is 5% in each one of these. And so basically view this as 100 universes. And so the 100 parallel universes, there's me running an experiment. So there's 100 parallel me's. I'm not running 100 experiments. 100 of me's are running one experiment. And so in all of these universes, the experiments that the 100 me's run happen to capture the true mean. But in these 5 universes up here, or 4, sorry, these 4 universes here, then I managed to run an experiment that's a dud. And the confidence interval I calculate for my experiment does not include the true mean. And so that is what I mean by having a false positive rate. And so 4 of the universes get bad luck, but 96 of them get, everything worked as we'd like. And that 5% error rate is the same across these, as I go up in samples, the error rate doesn't change. I'm still unlucky in 5 universes, but I'm getting more sensitive. I'm getting more statistical power. So up here, even though I'm still 5% unlucky, in the universes where I capture the mean, I have a much tighter band of possibilities for what that true mean is. So that's kind of the reason why we take more samples, is to get more sensitivity. And then, so on the flip side of that, if my experiment has more variance, but I don't change anything else. So if there's an additional source of noise in my experiment, then my confidence intervals are going to get wider with the same number of samples. So again, I've got the 100 universes. That's what I've simulated here. But in these 100 universes, I have a noise with a standard, or I have a true population with a standard deviation of 0.5. In this one, it's 1. In this one, it's 2.0. But I have the same samples in all 3 cases. And I had the same false positive rate, the same confidence level in all 3 cases. And in all 3 cases, as expected, I have a false positive rate of 5%. So there's roughly 5% of the universes don't have an experiment that leads in a confidence interval that captures the true mean. That's what we see here. But as I increase the variance in my population, I lose sensitivity, I lose statistical power. And so those confidence intervals that do capture the mean also include a much wider range of other alternatives which I cannot reject. And so that's what you're kind of dealing with here, is that we like to sample more to get more sensitivity. But as we're going to learn today, there are also ways to engineer your experiment to have less variance. So when you can't sample more, it's also good to try to engineer your experiment to have less variance. So that's kind of the new thing that we're trying to add, and that we will talk about a little bit more as we move on too. All right, so these confidence intervals are going to show up as you move on in your kind of statistical careers in a lot of different places. And so you should remember linear regression, from 380 and 385. And so you have a bunch of data points like these, and you fit a line through them. And so when you fit a line through them, that line up here is going to have an expression which has a slope and an intercept. And we are often interested in the slope of this line. So this is actually from a paper from a colleague of mine. And this paper, it doesn't matter too much about the details, but in this paper, they measured the CO2 production rate of ant colonies for different sizes of ant colonies. And so as the ant colony gets larger, then you can see how much CO2 ants are animals and they breathe. So they're expelling CO2, and you can use the amount of CO2 they expel to figure out how much energy they're burning. And so you end up getting this nice line here, but it's on a log scale. So this line with this slope of 0.78, because it's less than 1, that gives us the inference that as ant colonies get larger, then they actually burn less energy per unit ant or per unit mass. And so the mass specific energy rate seems to scale less than linearly. So there's a lot of speculation as to why this might be. Are the ants getting more efficient? Are there more idle ants? Et cetera. By the way, this also works with cells in your body. As you go to a species that's much, much larger, then their metabolic rate is much lower than you'd expect if all the cells were burning the same amount as species that are smaller. So, so that's kind of an interesting result. But the key point here that makes this interesting is convincing someone that this slope is less than 1. And so, just showing a single point isn't very convincing. So what did they do? Well, down here, they then they said, well, there was a slope of 0.78, and then they put right after that, immediately after the point estimate. The point estimate's just there to make the sentence flow. But then right after that, there is this thing that says 95% confidence interval, 0.671 to 0.898, which I've shown up here. And what you're supposed to notice as a statistician is that this confidence interval does not include 1.0. And so as they go on, this scaling exponent is statistically less than 1. And then notice this, degree of freedom, 27, t, p-value is that, so they just ran a t-test, a one sample t-test. That's what they're summarizing here. So for a degree of freedom of 27, so that basically has to do with the 28 colonies that they've got here. And so the degree of freedom of 27 gives you a t statistical value of 14.2, which if you look in a t-table, then it gives you a p-value that's less than 0.01, which is actually clearly less than 0.05. So what they're saying is that 1.0 is statistically significantly different than the data that they found, that they cannot support. They reject the hypothesis that this slope is actually 1.0. But then they go on further and they say, and it's not statistically different from 0.75. And then they again do a t-test here, and they show that if you test 0.75, it's not different. And what they're basically saying is that 0.75 is inside the interval. So they didn't actually need to do these t-tests. Simply showing me the confidence interval was enough. But just because it's convenient, then they ended up also doing the t-test. But showing me that the confidence interval overlaps 0.75 but does not include 1.0 is enough to say that you've rejected 1.0, but you've failed to reject 0.75. If you're wondering why 0.75, well, it turns out that one of the theories that helps explain this, what they call hypometric scaling, suggests that the real scaling rate for entities and bodies, ant colonies, whatever, should be 3/4. And what they're saying here is that their data is actually consistent with 3/4, but inconsistent with 1.0. So that's an example of using real confidence intervals to be nice, concise summaries of statistical results. And so this is, well, the reason I brought this up is it's showing you that confidence intervals meet linear regression. And so when you talk about a significant effect in linear regression, what you're saying is that your your slope of your regression line, you're traditionally saying is significantly different from 0. So normally you actually put a confidence interval on this slope, and you show that the confidence interval is does not include 0, that 0, which is way over here, is outside the confidence interval. That's the typical way you say that my regression line shows a significant effect. In their case, they wanted to do even more, where they wanted to show that not only do I get an effect of colony mass, but that effect is consistent with 3/4, but not consistent with 1. All right, does that make sense about this, this idea that a regression coefficient itself is a point estimate, and thus a regression coefficient should itself have confidence intervals? Any questions about that, about interpreting this data, these data? Okay. All right, let's see one more example of confidence intervals meet linear regression. This is from another colleague, and I won't go into the study, the important, or what's going on here, but I'll just mention statistically, this is the response variable up here that he was measuring in an experiment. And he was trying to figure out whether these things over here contributed to this response variable right here. And what he's done here in this table is he's just, the ones with stars are the ones that where he found a significant effect. In other words, this linear regression has these 4 independent variables and this dependent variable. So the linear regression, the regression line, has got this over here on the y-axis, and then it's got these 4 things kind of in the x-axis. It's kind of multivariate here. So this is x1, x2, x3, and x4. And each one of these has a slope, which corresponds to it. And that slope is how this independent variable ends up having effect on this dependent variable. And what he's showing here is that in 3 of these, the confidence interval does not include 0, but in 1 of them, it includes 0. And so in this one up here, this one right here, that one there is not significantly different from 0, which basically means that this particular thing does not seem to have an effect on this response variable. But these 3 confidence intervals do not include 0. These are all strictly negative confidence intervals. He's put the means out here just for convenience, but the confidence interval is really what the statistician looks at. And those confidence intervals all are strictly far away from 0. And he just reminds us of that down here. The star means that these are 95% confidence intervals that do not include 0. So because they do not include 0, they are significantly different from 0. And so these 3 independent variables are thought to have a significant effect on this dependent variable. So that's another way that confidence intervals meet linear regression. And you could imagine building similar tables for your simulations. Your simulations, you might have multiple decision variables, but you're not sure which one is important on this response here. Well, you could run an experiment where you test them all independently, or you could run a sophisticated experiment where you move them all, changing more than one at a time, and then use statistical methods to tease out their individual effects. And you'll learn more about how to do that if you ever take a formal design of experiments, DOE or DOX class, like something that Doug Montgomery would teach. And then you'd learn these multiple regression methods, and you would get tables that look just like this. So that's, I'm just trying to drive home how we interpret confidence intervals and how they really just are visualizations of t-tests. Okay. So any questions on that? Okay. All right. So the other rule that I want you to keep in mind is that you can then be shown 2 confidence intervals once we're doing relative performance. So you can get a confidence interval out of your as-is simulation, and you can get a confidence interval out of your modified simulation. And you normally would have to do a 2-sample t-test between simulations to say, does this simulation better or worse than this other simulation. But if you have those two confidence intervals, and it just happens to be that these two confidence intervals do not intersect. So, so that's what I'm sort of saying here is if this confidence interval, so if I lock this maybe, so if I've got two confidence intervals, one of them, which is over here, if I plot on a real line, and the other one, which is over here, and if there is a gap in between them, then that means that if this is for simulation A, and this over here is for simulation B, then what these confidence intervals are telling me, because there is no overlap, is that simulation A is significantly different from simulation B at a statistical level, at a significance level of 5%. So that tells me I don't even need to run my two sample t-test. Just by summarizing the confidence interval from one sim and then also from the other sim, seeing that they don't overlap means that they are different. They are significantly different, that this sim is a whole different beast than this sim over here that I have shown in effect. Now, the kicker is that if they do overlap, so if they intersect, then in those cases, you really do have to do a true two sample t-test. So if your confidence intervals are such that you have a confidence interval from simulation A, let's do that here, simulation A's confidence interval is over here, simulation B's confidence interval is here, and they overlap, so they share something right here, then that means that you got to discard those confidence intervals. They're not useful at all. You got to take the data and then run a true two sample t-test and then see if that two sample t-test has a p-value that's less than 0.05 or greater than 0.05. So there's no shortcuts there, unfortunately. Okay. And so I'm just showing that example of that. So here I've got two confidence intervals. So this is from I think real data from an HIV detection method. So we have method A and method B, and we have days until the detection. So with you're trying to see, does one method detect HIV in a faster time than the other method? If you just look at the point estimates, which are these middle points, you might conclude that detection method B is better because it detects it faster. But these overlapping confidence intervals should give you pause. And when you then run the real data into a two sample t-test, then what you find is that the p-value is 0.049. And from there you say, okay, that is less than 0.05, which means there really is a significant effect. So they overlapped here. And so because they overlapped, we really couldn't, you might've said, oh, they overlapped, so there's no difference. Well, in this case, there was a difference, but the only way to detect that was by running the test. That's why I'm bringing up this example. Okay, before I then move on, are there questions about that, about this rule for if I give you two intervals, and I might imagine doing this on a final exam, I give you two confidence intervals, and then asking you to conclude something about the t-test from those two confidence intervals. Does that make sense? Okay. All right. So, so kind of hinting at what we're talking about today, then, what we would like to do. So there was a question in the private chat that said, so this only applies for one sample CIs, question mark. And so yeah, these confidence intervals that I'm drawn here are the one sample confidence intervals. So I run a study, and just to be concise, I summarize the response variable that I get out of the study with a one sample confidence interval. And that is usually meant only for absolute performance. And so that way someone can look at this single confidence interval over here, and they can say that for the average, or for any given human who uses this HIV detection method, if they have HIV, it's definitely not going to take 34 days, and it's definitely not going to take 30 days, but it's going to take somewhere between 31 and 33 and a half days in order to get that detection. So that's this is a one sample confidence interval over here. So the question is, if I happen to have two one sample confidence intervals, what can I do with them? And if it just so happens that your one sample confidence intervals don't overlap, you can conclude without a two sample t-test whether that they're statistically different. But if your one sample confidence intervals happen to overlap, then there's no shortcuts. So these confidence intervals are one sample confidence intervals. And so the thing we're trying to build today is what we would think of as a two sample confidence interval. I hope that answers your question. If it doesn't, feel free to let me know in the chat. All right, so today we're talking about relative performance. We are going to introduce effectively a two sample confidence interval. So we are going to say, is there a way to summarize our two sample results in a just as compact and useful way as we can for our one sample results? And so we are going to build a confidence interval that looks like this one up here. And so this confidence interval here is effectively going to be a confidence interval on the difference between our two systems. So rather than asking, what is the confidence interval for X? What is the confidence interval for Y? How do those two combine? We are going to say, how do we build a confidence interval for the difference between X and Y? So that we can then say from this difference, we can treat, even though it's a relative comparison, as if it's an absolute comparison. So then our question will be, does our difference confidence interval include 0? If it does not include 0, we can conclude our systems are different from each other. And we can conclude in this case that X is greater than Y. If it includes 0, then we can't conclude anything. X may perform equally as well as Y. Or X and Y might be different, but the difference was buried in the noise and we just can't detect the difference, perhaps because our confidence interval is not sensitive enough. So that's what we're moving toward today. All right, so any other questions about confidence intervals before I summarize our new stuff about steady state simulations from last time? Okay. All right, so as we talked about 2 lectures ago, once we have the confidence interval, we now have a new way to determine how many samples we need in a simulation like a transient simulation where you need to figure out how many replications to run, how many full replications to run. And so before we used a power analysis like you did on homework G3, but now we can use a confidence interval. Instead of specifying a certain level of power, which is also related to sensitivity, we can instead specify a half width. We can either do that in percent of the mean, or we can do that in an absolute sense. And then you can use the formula for half width to then calculate the number of additional samples you need. I say additional because you have to run a pilot study to determine an estimate of the standard deviation in your system. And that estimate itself is going to be plagued by uncertainty. And so the number that comes out of this formula will itself maybe not be perfect, but at least is a good starting point. So then you run that many more independent replications, you can calculate your confidence interval there, and then hopefully it will be less than the criteria you were given. And if not, you add a few more replications and then you're usually okay. So that is one way to use confidence intervals to determine how many replications you need. Now, last time we introduced additional complications that are introduced only in the case of steady state simulations. So these are simulations where we have to get rid of the warm-up period because that introduces bias. And then so we have to determine how long of a warm-up period and also how long of a replication and then how many replications and if there's a way for us to trade replications for just running the simulations longer. And so we talked about that the one way to shorten the warm-up period is to intelligently initialize. So use like a queuing network model to determine what the proper initial conditions should be. And that should significantly reduce this warm-up period. Then we can use time series analysis, which is what we talked about last time, to try to then guess as to how long this warm-up period should be. So those were kind of our 2 ways to remove initialization bias. And I tried to emphasize, although maybe I didn't do it that well, that regardless of how many replications you run, your initialization bias will not be removed by adding more replications, because every replication has the same bias. And so if you just add more replications, you're just adding the same bias and they never average out. So adding more replications does not get rid of bias. Bias is fundamental, and you need to actually work with your simulation to get rid of bias. And so that means, like, you know, making a longer warm-up period. So, and so that's, we're saying, well, then how long do you run your simulations? And I gave you this rule that said, once you determine your warm-up period, then basically you run your simulations for 10 times longer than that period. So for discrete data, you can take your warm-up period and you want the amount remaining in your run to be at least 10 times your warm-up period. For continuous time, then you take your warm-up period and you just say your simulation is about 10 times the warm-up period. These are just basic rules mirroring what the book talked about. Now, once you've done that, once you have replications that are that long, then you can flip back and say, all right, well then now I've hopefully taken account of all of my initialization bias. And so now I want to reduce my confidence intervals to gain more sensitivity, more statistical power. So what do? I increase my number of replications. So increase them as much as you can up to computational limitations. So if it takes you a day to run a simulation, which some complicated simulations might, then running 25 of them means spending a whole month running simulations, or finding 25 computers to finish them in one day, or 25 cores of your computer to finish them in one day. And so, so you might not want to run more than 25. And it turns out that if you think about the T statistic, once you go over 25 independent replications, if you look at what happens to that critical T statistic, and if you think about what's happening to the standard error of the mean, they don't change that much unless you get huge numbers more replications, like 250 or 2,000. So instead of running more replications, there's a trick in steady state simulations where you can take however many more replications you want to run and further extend your end time. And that will not add to replications, but it turns out that will reduce the variance in each individual replication. And like I just said earlier, a few slides ago, if you have a way to reduce variance in your system, that is another way to gain statistical power. And so the trick is graphically shown here. If you can figure out that I ran this many in my pilot study, R naught, and I need to run this many R, so I want this many more replications, then, so in this R naught, it might be the 25 replications that you're going to run. And I'd say, you know, or maybe it'll be 10 replications, but, and you want to figure out, you know, how many, how do I get the same effect as running these additional replications? Well, if you scale your warm-up period up by this factor, and then you similarly scale the simulation length up by this factor, then what you're doing is you are just taking your pilot time right here, which is, this is your pilot simulation. You're scaling it up this way, and you're growing that initialization phase. And so not only are you growing the additional data you're collecting, so the data you're collecting here, that will likely reduce the variance from replication to replication. And the initialization phase, by throwing out more of that initial data, then you get rid of more initialization bias. So you're not only increasing the sensitivity of your experiments, but you're also getting rid of bias. And so that, if you have the computational power, then that is always good. Run longer simulations rather than running an exorbitant amount of those simulations, because you can further reduce initialization bias. Okay. All right, and then the one thing that I didn't get a chance to talk about, and this is the last thing in the review, is batching. Before I do that, does that make sense? Does this make sense right here? Because this is the last thing we ended on last time. This idea that you can trade replications for length, and that actually not only has the same effect as increasing replications, but has the bonus effect of decreasing bias. Does that make sense? I can imagine asking about that on a final exam too. Okay. All right. Now there is one other cool thing that we can do with steady state simulations, and only with steady state simulations. And that is the idea of batching. And I don't mean batching in the arena sense of batching of creating batches of entities. I mean creating batches of results from a single simulation. I mentioned back when I started to motivate this section that there's this kind of baking sheet analogy where if you have a sheet, you maybe can cut, if you're making, sheet cake or brownies or something like that, you can cut those into different brownies. And if the sheet is small enough, then all of those brownies will pretty much taste the same. Now, if you're in a giant industrial oven and you have a gigantic baking sheet, then some parts of the oven are going to heat differently than other parts of the oven. And brownies from other parts of the oven might taste different than brownies from this part of the oven. And so the entire oven, because it has heterogeneity, ends up breaking correlations from one part of the baking sheet to another. And so by cutting those things up, you actually do get independent samples, so long as you make sure that your samples are kind of far enough away from each other. And you can do the same thing in a single simulation. So you can run, and this is what I think Arena a lot of times likes you to do if you're doing steady state simulations, is just to run one replication, a single replication. And so it's not really replication, you just want one run of your experiment. And you run it really, really, really long. So you set the end time to be extremely long. And then you will discard some, which are the transient, because it's steady state simulation. And then you can then take data from within that time series. And so these are performance data you can measure. So this is like, what's the current queue length? What's the next queue length? What's the next queue length? And so on. And so you can take that over a long interval, and then you can treat that as if it was its own steady state simulation and put that away. And then in that same simulation, you restart. And we don't restart the simulation, but you just chop that same long time series into another little batch, like another little brownie. And then that becomes another piece of your simulation, another replication, but it's generated from a single replication, but we treat it like another independent replication. So really, these are pseudo replications. If these are short batches, then the parameter I estimate in this batch will be correlated with the parameter I estimate in this batch. You can predict one from the other. But if these are long enough batches, then the performance estimate I get from this batch will be independent of the performance estimate I get from this batch, and so on and so forth. And if in Arena you run your simulation for long enough, if you run one replication, you might notice this. Some of you might have noticed this so far. I hope some of you have. When you look at your report in Crystal Reports, it'll give you confidence intervals. And you should think, well, how the heck is it giving me a confidence interval? I only ran one. I cannot get a confidence interval with one. I can't estimate standard deviation with one. What it did was it assumed that since you only ran one, you are running a steady state simulation. And so it took all of your response variables, your performance measures that you have measured from the simulation, and it did this to them. If they were long enough, and it determines if they're long enough, but if they're long enough, then it will automatically chop them up this way. And then and it finds as big batches as it can in order for it to get independent replications while still trying to get as many replications as it can out of the single run. And then it uses those as independent replications for it to then calculate a mean and a confidence interval. So if you get things like where it says like insufficient, when it's trying to calculate, that means that you didn't run the simulation for long enough for it to be able to properly do batching. So if you like this approach and you're getting insufficiency for your confidence intervals, just run your simulation for longer in Arena, and eventually you'll reach a critical length where it will start, it'll say, it might say insufficient, but it might also say like means are correlated or something. There's another term that it uses, which basically means run them for longer. And it will then determine eventually, once it's safe, for it to chop them up and then treat your single run as a generator of multiple independent replications. Now, you of course have to be careful of this. This is a little bit like watching a TV show for and trying to make inferences about the demographic mixture of people just from the demographic mixture of people in the episodes of that TV show. This is like episode 1, episode 2, episode 3. You might notice that there's a shift in diversity from one episode to another, but if the episodes are very tightly correlated with each other, you know, if you're just watching Ally McBeal or something like that, then you might notice that there's not a whole lot of diversity there. And so it would be improper for you to make an inference about a larger population. But maybe if you watch a TV show over 15 different seasons, then you might notice that the characters start mixing in and out. And they start looking a lot different. And so in that particular case, you could go from season 1 to season 2 to season 3 to season 4. And the seasons are now large enough that you can treat them as independent samples of the larger population. And so for that long running TV show, the seasons are big enough batches that you can treat as an experiment where you're sampling the larger population. That's kind of what you're doing here. Okay. So, so that is what ARENA is doing. So before I get into slightly more details in the next 2 slides, before we go into brand new stuff, are there questions about any of that? Okay. So behind the scenes, what ARENA is doing is it's running a parallelogram. So in the output analyzer, you can, like in Lab 9, I can take a single replication out of your Lab 9 manufacturing system, and I can run this autocorrelation analysis, or a parallelogram, which is one of the graphs that you can graph in the output analyzer. And what this is showing me is as I get farther, as I take a performance measure, as I get farther away from that performance measure, how correlated is the performance measure that far away from the focal performance measure? So this is showing, this is basically plotting for every distance between performance measures, what is the correlation between those performance measures in a single run? And what this shows me here is that I have significant correlation for short distances, but that correlation gets small over time. And if this level of correlation, down here, if that is sufficiently small that I think this level of correlation could be generated just by noise, then in that case, I can maybe consider that my batches become uncorrelated with each other, say around here. Because I say around here, I'm pretty safe that all the correlations from here on out are all pretty small. And so I can treat that as a candidate batch size. And it turns out that to be safe, I don't want to like multiply that by like 10. Other programs like MATLAB, you can do the same thing. I can take that, you know, data, and I can, there is a function in MATLAB that generates a parallelogram. And it even is a nice enough thing where it actually plots those, that interval, where everything under that interval, this is under the null hypothesis of no correlation. If you were to generate a parallelogram, you would get correlation scores that would be in between this blue line and this blue line at the 5% significance level. So basically this tells me that after, say, a lag of 20, so 20 time units in my simulation, everything after that is effectively uncorrelated. And so once I figure out my correlation length in my simulation, then I can just choose a batch size of say 10 times that. So my so if it's 20 seconds, then I'm going to use a 200-second batch size. And then if I run my simulation for 2,000 seconds, I can generate 10 batches of that. I might still have to discard the transients. So discard the transients and then run it for 2,000, and then I can get 10 effectively independent samples out of a single run. Okay. So that's all of the stuff about steady state sims. Are there any questions about that? About the purpose of batching and how ARENA does batching automatically for you if you run a long enough simulation? Okay. All right, well then let's see how far we can get into relative performance analysis here. So as I mentioned before, now we're trying to build effectively a confidence interval that allows us to summarize the difference between two systems as opposed to building two confidence intervals, one per system. And so the idea here is we have two systems. And so I've got a call center operation that I'm simulating here. And in one of them, I simulate callers come in, they get selected to either go into billing or support. And this is maybe my as is system. And 41% of them go to billing, and it's about 60%, 59% go into support. And they're currently staffed with 7 operators, 3 in billing and 4 in support. Now, the boss realizes that if we could just cross-train everyone, all 7 of those, then to do both billing and support, then maybe the idle time that we're seeing in billing could actually end up relieving some of the strain that we're seeing on support. And so in that case, we would like to study the hypothetical change of cross-training these operators so that they all do the same thing and seeing how that changes the caller's experience. So those are the two systems that we are simulating in order to try to compare. Now notice here, I talk about relative comparisons. If you were just like, some of you when you're doing your final project might choose to just simulate one of these systems. And then you would then say, if I want to add one more billing operator, how much better is performance going to be? The downside of doing that is your model of simulation 1 has to be perfect for me to trust your performance increment in absolute matters as you're adding one operator. Alternatively, if I'm comparing a simulation that is this version versus the cross-trained version, I actually don't care if the absolute numbers aren't quite right, just so long as they capture all the salient features of the system and I can show that system 2 is significantly different, better or worse than system 1, then I end up doing the job. So these relative comparisons, there's often less burden on you, the simulation expert, and there's often more low-hanging fruit, more interesting things to say, more fundamental things to say. So the idea here is I'd like to build a confidence interval, which is the difference between these two systems. And that confidence interval, if it is strictly negative, so it does not include 0 and everything's negative, I will conclude that system 1, in whatever that performance measure is, let's say this is waiting time in the queue. Well, in this case, system 1 would be better. If, on the other hand, the confidence interval is strictly greater than 0, it does not include 0, and they're both above 0, then I conclude that system 2 is better. It has a less waiting time. If instead this confidence interval includes 0, then there's no evidence that I can use to conclude that one system is better than the other, and I might need to run more replications. So there are 3 approaches to generating such a confidence interval, which all tie to 3 different ways you can do 2 sample t-tests. So there's the paired approach, which is similar to what you did in homework G3. Then there are 2 independent replication approaches, which are going to be similar to more traditional 2 sample t-tests. One where we pool the variance and one where we assume that the systems have unequal variance. So if we get into that, and we're not going to complete all of this today, and so I want to at least get through the paired version here, is that what we can do is we can specially design, as kind of was done in homework G3, the experiment so that every outcome of the experiment is paired. So in a call center, you can make sure that you get the same callers going into both simulation 1 and simulation 2. It's as if you can rewind a universe and play it back with the same callers, but with a different call center. And so you could say one day's callers go in and I get the average wait time for those callers. Another day's go in, I get another average wait time. So every day is like a new replication, but I simulate the same day for system 1 and the same day for system 2. So the same callers from day 1 go into both systems and I measure the performance. The same callers from day 2 go into both systems and I measure the performance, and so on and so forth. And by pairing those outputs, what I do is I create a correlation in the outputs of the 2 different simulations. And the cool thing that does is if you look at the variance of 2 difference in means, then you'd use a little probability from like 385, I guess. And the variance of a difference is going to be the sum of the individual variances minus the covariance of those two, so how much they correlate to each other. And so if I break that up, this is my variance of my first system, this is the variance of my second system, and this here is a term with the correlation between them. And so what we're saying here is if I can create a correlation between my two systems, I reduce the variance in the difference in performance between those two systems. Practically what I'm doing is I'm basically saying that if I give us a tough set of callers to both call centers simultaneously, then I reduce the variance, which is due to just some days being a tough set of callers and some days being an easy set of callers. If I were to randomize the callers completely across my two call centers, I introduce more variance because just by bad luck, day one is going to be a tough set of callers for one call center, but it might be an easy set of callers for the other call center. So if I ensure that if one call center gets a tough set, the other one also gets a tough set. And then the next time, if one call center gets an easy set, the other call center gets an easy set. Then that guarantees that I'm not going to see the variance from the callers bleed out in the performance measures. All those will be subtracted out away so that I'm just focusing on the difference in performance. So regardless of what type of callers you get, then how much better is one over the other. So that's what we're doing here. But the thing here is by introducing a correlation between the outputs, I now cannot do a two-sample t-test. I have to use our paired difference t-test, which is what you did on homework G3. So whenever the outputs are paired, you cannot treat them independently. You cannot run a two-sample t-test on it. You have to generate a new measure which accounts for the pairing. So every output from system one that's paired with the output from system two, I generate a difference between those outputs, like you did on homework G3. And then I treat these differences as something I can analyze with a one sample t-test. And so at this point, all of the differences are independent from each other. So I can use a one sample t-test and test to see if the mean difference is significantly different from zero. So I'm going to calculate a mean difference. I'm going to calculate a variance of the differences. And then my standard error for those is just going to be the standard deviation of the differences divided by the square root of the number of replications. My degrees of freedom is just 1 minus the number of replications. And that allows me to give a nice confidence interval where it's just the mean difference plus or minus the standard error of the mean scaled up by that critical t value. And so I compare that thing to zero, and then that's how I compare my two systems. Very similar to how you did in homework G3. So that's the first type. Now, for the other two types, I think we'll summarize those in the next lecture. And those are, I think, where it's going to be kind of slightly newer material. And then I'll revisit the Bonferroni correction to finish up. So, but I think now is probably a good place to stop. So I'm happy to take questions, but let's close with an attendance exercise. So I will put the link in the chat. And the attendance question that I'll give you for to close out here is why is it inappropriate to use a two-sample t-test on data that on data from an experiment with paired replications? So that's the attendance question. Why is it inappropriate to use a standard two-sample t-test on data from an experiment where you've got multiple conditions and you've paired the outputs together? So what requirement is not met by the response variables as they're coming out of those simulations that makes it so that I can't use a two-sample t-test? And with that, that's all I've got for you today. Happy to stick around for a couple minutes for questions, but if you don't have any questions, you can feel free to head out. Okay. So far, I don't see any questions. Looks like now people are rapidly declining. So in that case, I will end the meeting and hope everybody has a wonderful weekend.